excited to have Jennifer on for this speaker from Georgia Tech. She's going to tell us about knots, groups, and
People in the back hear me? Great. Excellent. So today I'm going to tell you about knots, groups, and free manifolds. So I'm a low-dimensional topologist. I earned my PhD in Philadelphia 12 years ago, so a while ago. It's great to be back. The first sort of like public talk I ever gave was an expository talk at a graduate student conference, a lot like this. So I'm really glad to see sort of the next generation of mathematicians here doing the same thing. And at that conference, I met a lot of people who went on to become my friends and collaborators. So look around, talk to people. You might still be seeing these people, 5, 10, 15 years down the road. Okay. So I'll tell you about knots, groups, and manifolds. Great. So let's start with knots. So a knot for us will be a smooth embedding of a circle into S3. So you can think of S3 as R3 together with a point at infinity. And we study these things up to isotopy, so they're allowed to wiggle around. Okay, so what are some examples of knots? This is a knot. This is a smooth embedding of a circle into S3. This one's called the unknot. Some other examples of knots. This here is called the trefoil. And here's another knot. This is called a figure eight. There are some operations we can perform on knots. We can make new knots out of old knots. Probably the simplest operation is called the connected sum. So we just do this. Our knots are oriented, so there are little arrows on them. So we have to do this in a way that preserves the orientation. And that's a way to make new knots out of old knots. This is the connected sum operation. I once had a student refer to this as hashtag. Okay, so now we can look at the set of knots in S3 under the operation of connected sum. So anytime you have a set together with a binary operation, what's a natural question you might ask? Is it a group? Great. Okay. So is this a group? Well, let's see. What do we need to check to see if this is a group? Well, groups have to have an identity. Wait. So does anyone have a suggestion for what might be the identity in this group? Yeah, the unknot. Great. Yeah. So you can see. Well, if you connect some with the unknot, then up to isotopy, nothing has changed.
So how do I see this as something in S3? For example, this trefoil.
Oh yeah, how do you see these things as in S3, right? So these things, hopefully you don't see these as things in R3, right? And so you can think of S3 as R3 together with a point at infinity. So this is an R3 and somehow there's a point, taking the point at infinity. But we can just draw these things in R3. Great question. Other questions? Okay, so we have an identity. What else do we need to check to see if something is
Inverse.
inverses? Great. So let's see. Do we have inverses? All right. So unfortunately, the answer is no. And in fact, I'll prove that for you modulo some sort of facts that I'll just have to assume. All right. So there's something called knot genus. So this is the genus of a knot. It's the minimum over the genus of all surfaces sigma, such that sigma is what's called the Seifert surface for K. So what does that mean? that means that sigma is compact oriented surface such that the boundary of sigma is here not k. So it's called a Seifert surface. Okay. So maybe it's been a little while since you've seen surfaces and you don't remember what the genus is. And in fact, maybe you're also confused because, well, these surfaces have boundary. So if we care about compact-oriented surfaces without boundary, well, those are characterized as the homeomorphism by their genus, right? So you have a sphere, you have the surface of a donut, you have the surface of a fancy donut, etc. Great. Okay, and then, well, if you want to characterize compact-oriented surfaces with a single boundary component, it's basically this, but you just remove a little disk from them, and that's the characterization. And right, so this is genus 0, 1, and 2. Great. So it's a fact that every knot bounds some oriented surface, and then you just look over all surfaces that you're not bound, and you look for the one with the smallest genus. So that's the genus of a knot. So some examples. So what's the genus of the unknot? 0, right? Well, the unknot, it bounds a disk, right? It bounds this disk that you just see sitting at the board. A disk is homeomorphic to a sphere minus the open disk. So genus of the unknot is 0. Let's see, the genus of, say, this knot here. Wait, so here's this knot. It bounds this surface that, wait, so imagine you have surface here, and then at each of the crossings, imagine your surface doing a half twist. And so then each of these 3 crossings, your surface does a half twist. And so now we're going to see the other side of our surface. So our surface is blue on one side and red on the other side. So here's a surface. It's oriented. And then it's an exercise, for example, to use an Euler characteristic to check that this surface has genus 1. Using some knot invariants, you can also show that this knot is not the unknot. So that tells you, well, this genus, if it's not the unknot, it can't bound a disk, and it bounds the genus 1 surface. So this tells you that the genus of this knot is a capital 1. Okay, so that's some knot invariant. It's a way to assign a number to a knot. And so what are some nice facts about genus? Okay, so the first fact is that the genus of a knot is 0 if and only your knot is the unknot. And the second fact is that genus is additive under connected sum. So the genus of the connected sum of 2 knots is just the sum of their genera. Okay, and so these 2 facts are sufficient to conclude that we don't have inverses. Right? Because, well, if K is not the unknot, then fact 1 tells us that the genus of K is at least 1. Right? And, well, genus is always a non-negative integer. So if your genus is at least 1, well, there's no other knot you can add to it to get a knot with genus 0. So that means that it does not exist at K prime such that the genus of K maximum K prime. Okay, so we don't have inverses. That's a little sad. And well, I said I was going to tell you about proofs. So maybe now you're wondering, okay, well, is there something we could do so that when we look at the set of knots under connected sum, well, that we do get a proof? Right, so we've been looking at knots up to isotopy. For now, we'll study knots up to a weak weaker notion of equivalence, such that up to that notion of equivalence, when we look at knots and the connected sum, we do get concluded. So the weaker notion of equivalence we're going to consider is called concordance. Okay, so we'll say that two knots, K1 and K naught, are concordant if K naught and K1 co-bound a smooth annulus in S3 across the unit interval. So what do I mean by that? Well, S3 plus the unit interval is 4 dimensions, so I'm going to have to draw a picture that's a lie to you, but is sort of hopefully capturing the essence of what's going on. Okay, so imagine you have S3 plus the unit interval. Well, on one end, you'll see S3 plus 1. Okay, so that's just homeomorphic to S3. And then similarly on the other end, you'll see S3 plus 0. So in the S3 plus 1 end, well, you'll see some knot K1. And in the S3 plus 0 end, you'll see some knot K naught. And then in this S3 plus I, an annulus is homeomorphic to a cylinder. So you'll see a cylinder, right, whose boundary on one end is your knot K1, and on the other end, the boundary is K naught. And if such a annulus or cylinder exists, then we say that these knots are concordant. This is an equivalence relation, right? So to be an equivalence relation, you have to be reflexive, symmetric, and transitive. To see that this is reflexive, you can just take your cylinder to be your knot cross I. Right? Take a knot cross I for the individual cylinder. To see that it is symmetric, well, you can just take your cylinder and just like turn everything upside down. So that's how you can see this is symmetric. And to see that it's transitive, well, you have two cylinders, you can stack them on top of each other, and then, okay, maybe you're unhappy, the interval now goes from 0 to 2 instead of 0 to 1. You know, there are ways to fix that. Okay, so this is an equivalence relation. Maybe you want to see an example of a concordance. So, I'll first draw a knot in S3 and I'll draw some surface, but somehow that surface is going to help us visualize an example of this. So let's take our knot to look like this. So here's my knot. I've drawn it in a way that, maybe with a little imagination, you can see that this knot actually bounds an immersed disk in S3, right? So there's this disk here, and then it's also here. So it's immersed because it intersects itself in these two arcs of self-intersection. One of them is right here. One of them is right here. Okay, so, right, so in particular, this is not a ciphered surface for K because ciphered surfaces have to be embedded. This thing is immersed, it intersects itself. Okay, this is called a ribbon disk. The ribbon disk in S3. Okay. Great. So just like the two spheres, the boundary of the 3 ball, well, S3 is the boundary of the 4 ball. So now let's think about S3 as the boundary of the 4 ball. We have this ribbon disk sitting in S3. Well, let's push this a little bit into the 4 ball. Like, you can imagine something sitting on the surface of a basketball, you can push it a little bit into the basketball. have these nice arcs of self-intersection. So you have this surface here, you pushed it a little bit into the four ball. Well, if you just push this part so deeper into the four ball, then you can get rid of these arcs of self-intersection because you have this extra degree of freedom. Just push this sheet deeper in away from this one, and then the self-intersection goes away. Just like you can imagine, like I've been drawing these not crossings in the blackboard, and in the blackboard, well, sort of the arcs are intersecting. But if you allow yourself to go behind the blackboard a little, you could get rid of the self-intersections. It's the exact same idea. Okay, so you have this. This is immersed. Right. Okay, so now, well, this bounds. So now R naught K bounds an embedded disk. In the core wall. Okay, so now I'll draw another cartoon. So here's the four ball. The boundary is S3. Maybe here is my knot. Right, so everything is kind of down a couple dimensions. So I'll draw my knot as an S0, which is just 2 points. And this bounds a disk. Right, so this is my disk. Okay. And now, well, if you have a disk, think about like the unit disk in the complex plane. If you remove a neighborhood of the origin, it becomes an annulus, right? So I have this disk here. So if I just remove the neighborhood of a point, say here, right? Well, the disk becomes an annulus. And if I have the four ball and I remove the neighborhood of the point from the interior, that becomes S3 cross I. Right, so maybe it's hard to see it in this dimension, but think if you have a basketball and you remove like a neighborhood of the point in the middle, then that becomes S2 cross I, where I is the radial dimension. The same thing is happening here. Okay, so we remove a neighborhood of a point in this. Well, what do we get? Well, we started off with the four balls together with the disk, and now what we end up with is S3 cross the unit interval, comma, an annulus A. So now this becomes a concordance. So what I've just shown you is that this knot K is concordant to the unknot. Yeah, question?
I still could see your basketball example when you take out.
Okay, still can't see the basketball example I'm taking. Okay, so maybe let's look at the example of, let's go down one dimension more, right? So let's take a disk, right? So if I have a disk, right, and we remove a neighborhood of the origin here, well, the disk becomes an annulus where, right, so we have the radial direction here, right? What's left is S1 cross I, where here's S1, and this is the I direction is in yellow. And so now you can do the same thing with the basketball, where the I direction is going to be the radial direction, like the direction coming from the center out to the end. Other questions? Okay. So knots that are concordant to the unknot are pretty special to us, so they're going to get a name. They're called slice knots. So a knot K is slice if and only if K is concordant to the unknot, which is equivalent to saying, by sort of this picture that I drew over here, which is equivalent to saying that K bounds a smooth disk in the four ball, right? I showed you how to go from the smooth disk to a concordance to the unknot. Well, if you have concordance to the unknot, you can basically just like fill in the unknot with the disk and fill in one of the S3 cross I, basically fill in the part that you cut out. That's how to go back in the direction. Okay, so this is great. We have this equivalence relation, and I claimed that this equivalence relation is going to solve all of our problems and turn knots and independent sum into a group. We're missing inverses, so I need to tell you how to get inverses. So here's the fact. K connects sum, the reverse of the mirror image is always twice. Great, so let me tell you what the reverse of the mirror image is. So if I have a knot K, well, I can change all the crossings. I can change any I can change all the over crossings to under crossings and vice versa. That's the mirror of K. And I can also change the orientation. That's taking the reverse. Okay. And so then, okay, so this fact tells us that the inverse of a knot is in fact just the reverse of the mirror image. Right? Because what is the inverse? The inverse is something that you connect sum with your element to get the trivial element. Well, in this case, the trivial element is anything in the equivalence class of the unknot, and those are exactly sliced knots. And so, well, in order to see this fact, I'll draw a picture for you that maybe is, a lie because it's down a dimension or two, but then that will sort of illustrate what happens. Okay, so let's imagine I have, okay, so here I have an arc sitting in the plane. Okay, now I can think about the plane as being the boundary of some, say, well, in this case, a box. And I can take this arc, and I can swing it through here until it comes back out here. So I'm taking this arc and swinging it around until it comes back out here. And if I take an arc, you just take an arc, take a piece of string at two ends, swing it around. It sweeps out a disc, right? You sweep out a disc right here. Okay. So now, well, what's going to happen? You should think about the top of this as being S3. You should think about the rest of this as being the four ball. So you should think about, okay, so here's a knot, and here's the reverse of its mirror image. Okay, and then here's the connected sum. Okay, so that's the connected sum. So you should imagine, well, here's an arc, right? This take that, sweep it through the four ball. If you think about orientations and everything, it's going to come out to be the mirror image of it. So you take this and you sweep it out in the four ball. And just like in this picture, when you sweep out an arc, you get a disc. Well, you sweep this out and you get a disc. So this is the truth that K connects some the reverse of its mirror image bounds a disc. Okay, so we have inverses. So, so this gets us to the knot concordance code. So the knot concordance group is usually denoted with a strict C. It consists of knots in S3 and a connected sum, modulo the implicit equivalence relation of concordance. Okay. So anytime you have a group, well, probably start to wonder, what does this group look like? So what are some questions you might ask about your group? You might say, okay, well, are there elements of infinite order? Are there elements of finite order? So, well, to answer that first question, are there elements of infinite order? There's this knot variant called the knot signal. the even integers. Okay, so to a knot, it assigns an even integer, and the fact that this is a group homomorphism means that it respects your group operations. So if you add two knots to take the signature, well, it's the same thing as taking the signature and adding the signatures. Okay, and it turns out that the signature of the trefoil is -2. So this immediately tells us that the trefoil is infinite order in the concordance group. Right, because this tells us that no non-trivial multiple, if you take a connect sum and connect, and if you take a trefoil and connect sum with itself, well, since this is a group homomorphism, right, connect sum of the trefoil with itself, it's going to have signature -4, which isn't 0, which tells you that your knot is not sliced. So no multiple of the trefoil is sliced, and so the trefoil is infinite order in this group. Okay, so we have elements of infinite order. That's great. What about elements of finite order? So let me tell you this nice fact, or I'll leave it as an exercise. Okay, so here's the figure 8. Here's the reverse of the mirror image of the figure 8. So I changed all of the crossings and I reversed the Schmidt orientation. So it's an exercise for you to do when you know you're bored, to check that these are actually isotopic, right? So you can move these strands around in such a way that this picture becomes this picture. And the other fact I want to tell you is that this knot, figure 8, is not sliced. So these two facts together, well, this fact, right, this is the figure 8, and this is the reverse of the mirror image of the figure 8. So here we have a knot that is its own inverse, and it's not trivial in our group. Great, so if you have an element that is its own inverse and is not trivial in your group, what's the order of that element? Yeah, that element is going to be order 2. So this tells us that the figure 8 is order 2 in the knot. Okay. These are some nice examples. Right? I mean, so the way I do math is I kind of do some examples and then, well, we're mathematicians, so you eventually have to prove things. So eventually then you want to study things more systematically. And so that was something that Jerry Levine did in the 1960s. He studied this group systematically using something called the Seifert form, right? So every knot has a Seifert surface, and then you can look at something called the linking form on that Seifert surface. Basically, you take some curves on that Seifert surface, and you look to see how they intersect one another. So Jerry Levine, in the 1960s, he used the Seifert form, so this intersection form on the Seifert surface, to give a surjective homomorphism from the concordance group to z to the infinity plus z mod 2 to the infinity plus z mod 4 to the infinity. So if you have a group that surjects onto an infinitely generated group, that tells you, for example, that the group that you started with has to be infinitely generated. So that's one consequence of this. Great. We've seen examples of elements of infinite order. We've seen examples of order 2. You might ask yourself, well, this part, does this tell us that there are elements of order 4 in the concordance group? And unfortunately, it doesn't, right? So for example, right, there's a homomorphism from z to z mod 4, just taking everything mod 4. And that's a surjective homomorphism, but every element in the universe is infinite order. Some other things, you can play this same game of looking at, well, we were looking at knotted S1s and S3. More generally, you can look at knotted SNs and SN plus 2, that's sort of higher dimensional knot theory. And in higher odd dimensions, you can do the same, do the same construction. And in those in higher odd dimensions, this is in fact an isomorphism. Whereas in this classical dimension that we're talking about here, this map has non-trivial kernel. Okay, so Levine's homomorphism relies on the following facts. Okay, so to a knot K, we associate some Seifert form B. Right, it's a bilinear form on the first homology of the Seifert surface, but you know, for this talk, just think about this as some algebraic gadget. Okay? That's where it sort of comes with linear algebra. If you trace through his construction, it follows that, well, if you take the reverse of the mirror image of K, you get a bilinear form that's very closely related to the one that was associated to K. In fact, it's just the negative of that bilinear form. Similarly, if you take the connected sum of two knots, well, what form gets associated to the connected sum? It's just the sum of the forms that were associated to K1 and K2. And by sum, I mean algebraic sum. And then lastly, if your knot is sliced, so if your knot is the trivial element in the concordance group, then it turns out that B has a nice, this bilinear form has a nice algebraic property. That algebraic property is that it's metabolic, which means that it vanishes on a half-dimensional space. So that's called being metabolic. Okay, so then what Levine did with this set of observations is he said, okay, well, you can look at these set of bilinear forms under the operation of direct sum. That's going to form a monoid, much like knots under connected sum form the monoid. And then right, so when we look at knots under connected sum, we're missing inverses. So we quotient it by the equivalent relation of concordance. And so, well here, let's look, we can look at the set of Seifert forms under the operation of direct sum. And then you can quotient by the equivalence relation, quotient by these kinds of forms, ones that sort of correspond to sliced knots. So you quotient by metabolic forms. And this turns out to be a group, just like the knot concordance, just like when we quotiented knots by concordance, we got a group. This is the homomorphism that he defined, right? So you have a knot K, and you just send it to the equivalence class corresponding to the same group. And then, well, Seifert forms, right? They're bilinear forms on Z to the N, and so what Levine did is he converted this into sort of a linear algebra problem, and then he was able to show that this algebraically defined thing is isomorphic to Z to the equality plus E minus E. Okay, this is great. This was done in the 60s. There's still lots of mathematicians studying this kind of stuff. So at some point, people define other concordance homomorphisms. So maybe that's the next question I want to address. Is what other concordance homomorphisms can we define? Okay. So about 20 years ago, Peter Oshoff and Sultan Szabo, and independently J. Rasmussen, defined something called knot-form homology. So this is a knot invariant, right? So it's a knot invariant, so that means that if two knots are isotopic, then they have the same knot flow homology. What did this invariant look like? So to a knot, they associated some algebraic object. In this case, the algebraic object is a chain complex. But you can take, maybe you've seen chain complexes in algebraic topology. Maybe you've seen chain complexes over vector spaces. These chain complexes happen to be over polynomials. Right, so a chain complex is a vector space or a module together with end of the self map that squares to 0. And these chain complexes are related. So depending on how familiar you are with different algebraic things, if you know what a chain complex is, great. If you don't, you can think about this as a vector space with some extra structure. For the point of view of today, that's fine. So they get this algebraic gadget. The chain complex maybe depends on how you describe your knot, but the chain homotopy type of your chain complex is a knot invariant. So in particular, say the homology of this chain complex is a knot invariant. Okay. But we're interested in knots up to concordance. So maybe we're interested in knots up to, and in fact, so the bad news is that there are concordant knots that have inequivalent knot flow complexes. So the knot flow complex, just sort of as it comes to you, is not going to be useful for concordance. But if you have an algebraic object, you can look at your algebraic object up to isomorphism, or you can look at your algebraic object up to some weaker notion of equivalence, right? And so if you look at this algebraic gadget up to some weaker notion of equivalence, then it is going to be a concordance invariant. So what do I mean by that? So we're going to play a game a lot like the game that we played over here. So to a knot K, we get some algebraic gadget. Right, it's a vector space with some extra structure. The construction is very nice. So in particular, if you take the reverse of the mirror image, right? This is a concordance inverse of K. Well, you get an algebraic object that's very closely related to the one that was associated to your original knot. It's the dual, right? So, right, if you see vector spaces, vector space B, you replace them to the dual vector space. It's just, in this case, since our chain complexes are over this polynomial ring, this is what I mean by the dual. But it's the exact analog of just taking the dual of an ordinary vector space. This should be somehow related to the knot flow complexes for K1 and K2. And it is, right? So there's lots of ways to take two vector spaces and get a new vector space. The one that's going to happen here is going to be tensor product. So just a tensor product of their knot flow complexes. In this case, you're taking the tensor product over the ground right here. Okay, and then if we're trying to do everything in an analogy to what happened over here, here in the Levine setting, then I guess we also need something nice to happen if our knot is sliced, if our knot is a trivial element in our group. And if K is sliced, it turns out that it's not flow complex. This algebraic gadget you associate to it has a particularly nice form. It looks like the knot flow complex of the unknot direct some other gadget, which I'll just call A. So it splits the direct sum as of the knot flow complex of the unknot plus some other thing. So this is called a local trivial. Okay, so what Oswald, Sauber, and Rasmussen showed is that this chain complex of chain homotopy equivalence is the knot invariant, and then sort of what follows here is that you look at these chain complexes up to a weaker notion of equivalence, and then you're going to get a concordance invariant. So if you look at the set of these knot flow complexes, okay, the binary operation we're going to put on these things is tensor product. Okay, and then we're going to quotient out by some equivalence relation called local equivalence. And just like what happened over here, well, if we do this, right, so then we get a group, which comes from the knot flow complex CFK, so I'll denote this as this. CFK. This is a group, and in fact, we get a concordance homomorphism. So just to a knot K in the concordance group, well, to that, that just gets sent to the equivalence class of its knot flow complex. Okay. So now, okay, so we, in some sense, succeeded in our goal of building more concordance homomorphisms. We had this knot concordance group. We had this homomorphism to this sort of algebraic mess. This group is sort of hard to understand. So then, so this group CFK is hard to understand. However, we can then look at some homomorphisms from that group to other simpler groups, and that can help us study the non-concordance group. So we have this non-concordance group here, and there's in fact, surjective homomorphism from this group to z to the infinity. So this homomorphism comes from the family of homomorphisms called PI. Okay, so this is defined by Irvin Dye, myself, and Max Alfred and Tom. And so as an example, PI of the trefoil, it's 1 if I is 1, and it's 0 otherwise. And so, wait, so now we have these homomorphisms. We also have Levine's homomorphism. And one nice application of these homomorphisms is that they allow us to study the difference between the smooth concordance group, which is what I've been telling you about, and the topological concordance group, which is what you get if instead of requiring your disk and your annuli to be smooth, you just require that they're what's known as topologically locally flat. So one application is understanding the difference between the smooth concordance group and the topology. Okay. And maybe the last thing I want to say about the concordance group is to leave you with this open question, right? So we saw that there's elements of order 2 in the concordance group. This open question that I want to leave you with is there other torsion in the concordance group? So is there n torsion in the concordance group for n not equal to 2? Okay. So I also told you that I was going to tell you about 3 manifolds. So we're going to talk about 3 manifolds. Can someone name me a 3 manifold? S3. Great. Can someone name me another 3 manifold? R3. Great. Terrific. I'm going to give you some adjectives. I'm going to say closed, connected, and oriented. So closed means compact without boundaries. So I guess we're going to, sorry, I want our manifolds to be compact, so by R3. But S3. Great. Other 3 manifolds that are closed? S1 cross S2. That's great. T3, which is S1 cross S1 cross S1. Great. Other 3 manifolds? Lund space, LPQ. Great. Other 3 manifolds? Not complements. Closed means compact without boundary. So we don't want boundaries, so we don't want not complements. But not complements are a good starting point for a family of manifolds. Okay, so I'm going to draw a not complement. So I just draw a not. Right. So not complement means you have a not and you remove the neighborhood of it. So I had the figure 8, and then this is to indicate I took out the neighborhood of the figure 8. So if you take a not complement, well, the boundary you're left with is a torus. And I said no boundary, so you need to get rid of the boundary. So what's one way to get rid of the boundary? Well, let's glue a solid torus back in. Okay, if we glue it back in the same way you cut it out, then we didn't do anything interesting. But we can glue it back in a different way, and that's called knot surgery. So that's S3. We cut out our neighborhood of K, and then it turns out the different ways to glue your solid torus back in, they're parameterized by the rational numbers. So the rational numbers are just telling you sort of the map from the torus to itself. So that's knot surgery. Great. And there's lots of other 3 manifolds. Maybe I'll tell you one other family called sigma PQR. So sigma PQR. Okay, so this is going to be happening in C3. So let's look at the 0 set of the polynomial x to the b plus y to the q plus b to the r. But let's not just take that 0 set. So this describes some set of points in C3. And then let's intersect this with a little sphere sphere centered at the origin. So C3 is R6. So a unit sphere in R6 is 5-dimensional. So just take a little 5-dimensional sphere centered at the origin. I intersect it with the zero set of this polynomial. Sort of all the intersections transverse and nice. So this turns out to be a manifold. Right? This thing is 4-dimensional, and it's intersecting something 5-dimensional and 6-dimensional space. So you do the codimensions. It is going to be 3-dimensional. So at least I'm telling you it's reasonable. And this then turns out to be a manifold. It's a 3-manifold called sigma PQR. As long as that roller strip to PQ and R being relatively defined. And then this thing is called the free-star topology sphere. So here are lots of 3 manifolds. We're going to just care about integer homology spheres. So a 3-manifold Y is an integer homology sphere if it has the same integer homology as S3. Okay, so which of these examples are integer homology spheres? This is sensibly named, so this in fact is an integer homology sphere. So this is an integer homology sphere. Maybe the very first example of an integer homology sphere should be the 3-sphere itself. Wait. So this is an integer homology sphere. This is not an integer homology sphere. This is not an integer homology sphere. Surgery on a knot. If P equals 1, then this is an integer homology sphere. Okay. So we're just going to study integer homology spheres. And then we're going to, okay, so we have integer homology spheres. I've given you some examples. One way to get new integer homology spheres from old integer homology spheres is to take the connected sum. So the connected sum of 2 integer homology spheres is again an integer homology sphere. So we have a set integer homology spheres. We have a binary operation, connected sum. Okay, and now, what have we been doing like all day? We have a set with the binary operation. Is it a group? Right, it turns out this is not a group, but okay, all day we've been getting, sets with binary operations that aren't groups, and then we've been quotienting them by some equivalence relation that makes it into a group. So we're going to quotient this by something called homology cobordism. And then this does turn into a group. So 2 3-manifolds, Y0, Y1 are homology coordinates. If there's a smooth 4-manifold W, compact, such that, Y0 and Y1 should be coordinate, and W should be the coordinates in between them, which means that the boundary of W, there's some orientation to happen, so it's minus Y0 disjoint Y1. That's the coordinate part. And the homology part is a little technical. It means that W, on the level of homology, looks like a product. So that means, one way of saying that is if you look at the map induced by inclusion on first homology, is that on the level of homology, W looks like a product. So one example of a homology coordinate is just for W to actually be the product. So an example of a homology coordinate is you take W to be Y cross I. Another example of a homology coordinate, well, let's say that K naught and K1 are concordant, right? So that means that we have this cylinder in S3 cross I. Okay. Well, just like I described knot surgery, as you remove a neighborhood of your knot and then glue it back in a different way, you can take this annulus here, you can cut it out and glue it back in a different way, such that when you do that, on the ends you're going to get surgery on your knot, and then you're going to get some core manifold that actually turns out to be a homology coordinate. So the point is that actually if you have two knots that are concordant, well then their surgeries are homology coordinate. So there's a close relationship between knot concordance and this homology coordinate. Okay. So this thing up here, this thing is the homology coordinate group. It'd be nice to know things about the structure of this group. And one way to understand the structure of this group is to play the same game we played with the knot concordance group. Right, so the knot concordance group, well, one thing we did, you could look at these knot flow complexes modulo some equivalence relation, and you got all these homomorphisms. And you play the same game here. I guess, wait, so what's the identity in this group? S3, yeah. Yes, the identity is S3. Can people make an educated guess as to what the inverse of Y is? Think about, like, for a knot, we took the mirror of it, which was like reverse. We basically kind of in some sense like reversed the orientation on our knot. And so in here, well, it turns out that the inverse of Y is minus Y. You just reverse the orientation of it. Okay. So it turns out that there's this package of three-manifold invariants called involutive Hager-Floor homology. This is defined by Hendricks and Van Alsten. Wait, so to a three-manifold Y, we get some, it's a chain complex with some extra structure. That structure is a homotopy involution. But you can play the same game that we played before, right? So to minus Y, well, you get the dual. If you have the connect sum of two three-manifolds, you get the tensor product of these things. And then if your three-manifold is homology coordinate to S3, something nice happens. So this is what's called local trivial. So we play the same game we've been playing all day. So we look at these algebraic gadgets, which are called iota complexes. We look at these under tensor product. We quotient out by some equivalence relation. This turns out to be a group. We get a homomorphism from the sort of topological thing we're trying to study to this more algebraic thing that we have a hope of understanding better. That homomorphism just sends your three-manifold Y to the equivalence class of its chain complex. Great. And so then, using these techniques, Ergen and I, Max Stockton, and Lynn Schwung, were able to prove sort of the strongest known to date result about the structure of this group. So, here we go. The homology coordinate group is isomorphic to Z to the infinity plus some other group G. Great. So this is the best known to date result about the structure of this group. And so what I'll leave you with is the following open question. Right, so it was known before this result, but it's a corollary of this result that there's elements of infinite order in the homology coordinate. And so what's the natural question the question you might ask about the structure of this group? Yeah, the elements of finite order. And so it's an open question, is there any torsion in the homology coordinate group? And, okay. I don't want you leaving this talking that everything is hopeless. So let me just sort of tell you one sort of tantalizing fact, which is that this group I, for which we have a homomorphism from the homology coordinate, we have a homomorphism from the homology coordinate group 2I. So this group I does have two torsions. But we don't know that those elements in I are in the image of elements from the homology coordinate group. And moreover, even if you had an element of order 2 that was in the image of something, we don't know that we'd have to realize that something that's actually of order 2. So maybe the thing that would be great if we could answer is, well, can this two-torsion element be realized as coming from a three-manifold? And we want that three-manifold to be order 2. So we want minus y to be homeomorphic, or at least homology coordinate to y. So this would be a great question to answer. So I'll leave you with that. What's an example of a knot that's embedded in S3 but not R3? So I required all of our knots to be smooth. So in particular, they're tame. So, like S3 is R3 together at the point at infinity. If you have a smooth knot, or more generally a tame knot, it can't. That map from S1 to S3 cannot be surjective. That's just like a fact about sort of nice enough embedding. And so if it's not surjective, it always misses some point in S3, and by convenience, we choose the point at infinity to be one of the points that is missing. So if you allow yourself wild knots, which think of like a space film curve, then maybe you run into problems, but we just say, oh, that's like too complicated for us. We require, like my particular brand of knot theory requires all of our knots to be smooth, so they always miss at least one point in S3. So we just shove that point off to infinity and say, smile and say.
So to clarify, so is that
that in the non-concurrence group, we know that so there are no elements of finite order other than 2 or 4, but it's still open if there's any element in order 4.
But yeah, so we have elements of order 2, and it's
Yeah.
unknown whether there's other elements of finite order. Yeah, it's one of the very frustrating basic
Yeah,
questions.
I mean, so there's, it to say, so there no, if there are other orders, so you can only be 4.
Oh,
Because,
no, you could have elements of other order, but you would need some tool that's different than the mean homomorphism in order to detect it.
like, I'm kind of confused because you said so, like, there's a map, like, Z infinity and Z2 and Z4 stops. So, what does that Z4 mean? Yeah, what does it mean?
Yeah, all known elements that hit that Z4 are actually infinite order.
Oh.
Right, just like give a map to Z to Z mod 4, and
Oh,
just take that and
I see.
mod 4. Yeah, is the figure 8 the only example you know of order 2? No, there's infinitely many. So the figure 8 is one example of a knot that's isotopic to the reverse of its mirror image, but there's infinitely many knots, in fact, that are isotopic to the reverse of its mirror image. And in fact, of those ones, like a bunch of them are not, like infinitely many are not. They're linearly, they're distinct in concordance.
So you have constructed a chain complex from homogeneous spheres, and you have constructed a chain complex from knots.
I'll show this off, and then
Up to some degree, so and we have shown that complements of knots, like taken complements of knots, are homogeneous spheres. Like the SVQ.
Oh, yeah, yes, surgery and knots. Yes.
Surgery. So is there a relationship between the complex when you get from the surgery knots to the complex that you get from the knots?
Yeah, there is a relationship. That was in sort of some of the early papers with Oswald Sacco, and that's sort of one of the powerful aspects of sort of this Knotzel complex, is it can tell you the Hager-Floyd homology of surgery. Oh, yeah, you can, I can give you like an explicit description of these. Say that? Is there a relationship and the genus of the noun? Yeah, they're the same, right? Since the concordance, or the concordance inverse of K is minus K, and the genus of K is minus K.
You mentioned at some point that there is a difference between slice notes with a significant integrity, the topological integrity. Is there something here that let you understand that more?
Yeah. So this sort of not Floyd invariance, but all smooth invariance, whereas Levine's homomorphism was actually like a topological. And so, yeah, these invariants can sort of particularly be non-trivial on things that topologically are trivial.
For this group G, do we know anything?
Oh, for this group G, do we know anything? Not really.
Understand the relation between knots and free manifold correctly. You have a group from the components to the whole group.
Oh,
You have a group.
wait, so you have this fact,
Yes.
but actually, it doesn't, you have a set graph, but it doesn't respect connected sums. So the problem is that surgery on a connected sum is not the connect sum of surgeries. There's another way, so I described one way to go from knots to three manifolds for surgery. Another way is by taking a branch cover. And if you do that recipe for going from a knot to a three-manifold, then you actually do get a homomorphism.
Only connection.
Say again?
Is that one of the only few connections that you don't see?
Oh, between knots. There's lots of connections between knots and three manifolds. Yeah, I guess like, so for example, every three manifold is surgery on something. Every three manifold is a branch cover